And without further ado, it's me talking about hardware security. Also, happy International Women's Day. That's cool. Yes, Liz. Yippee. Okay. Hardware security? That's the real question. This is me. Move the captions. I think they're good there. They don't get in the way of anything. And do people have a problem with where the captions are? Okay, cool. I'm Kasey. If you don't know me, maybe this is your first general meeting because I'm here every week. I'm on RITSEC and RITSEC keyboard. I'm a little climber. Ash is not here, but they would say I'm sick and swag. Hardware learner and enjoyer, and I'm trying my best here. So what are we going to talk about today? We're going to build an understanding. We're going to talk about basic electrical components. Most of you have probably learned about those things in like Physics 2, or if you've ever taken a circuits class. We're going to go into logic gates. Most of you should know like logical math through like discrete or like subnetting. And you touch on it in 201, I believe. We're going through circuit diagrams and some boards. What is hardware and exploitation and vulnerability things? Exciting. Cool. So, it's not going to let me expand this window. It's fine. Okay. Basic electric components. Transistors. Transistors are semiconductor devices with 3 connections capable of amplification and rectification. That's cool. Did you know that the only 2-terminal transistor is a diode? So crazy, so cool. In this picture, this is a transistor, and you can actually stack them to make different functions in different devices, which we'll get into. We have capacitors. I wanted the clicker with the laser pointer, but I'll just point. This is a capacitor. Capacitors are a 2-terminal device that store energy in the form of an electrical charge. They consist of 2 electrical conductors that are separated by distance. Usually between that distance is either like a vacuum or some sort of like insulation. We have inductor, which is right next to the capacitors. Inductors are components that store energy in a magnetic field when electricity flows through it. A good way of thinking about capacitors and inductors is if you have a light bulb and you have a capacitor right before the light bulb and the light bulb's on. Whenever the electricity, like the voltage source, is turned off, the capacitor will slowly release energy to keep the light bulb on. So slowly the light bulb will go from bright to dim until the capacitor runs out of energy or voltage. With an inductor, the inductor will collect all of the energy in the circuit and the light bulb will be on. And then whenever the voltage source is cut off, there'll be a bright burst of light through the light bulb and then it'll die out immediately. So it's like on and then off, and then a capacitor slowly turns off. Super cool. Resistors, electrical components that limit and regulate flow of electrical current. If you guys are, for industry, resistors are really important to regulate the flow of voltage and current. For example, if I have a project that I'm working on that has to integrate with a project that Raina's working on, say my project intakes 20 volts and Raina's can only take like 7 volts. I would put in resistors to have a space where it has to connect. So that way the output voltage of my component is 7 volts and as much as Raina's component needs. So that's cool. And then a diode is a 2-terminal semiconductor device that allows the flow of current in only one direction. This is the diode. That's cool. It goes from positive to negative. So if you think of an LED, LEDs actually only flow in one direction. So if you have an LED in a circuit and it's on while the voltage is on, that means it's flowing from positive to negative. If you turn that LED around in the circuit, it's not going to turn on no matter how much voltage you're passing through it because it's in reverse bias, which basically means that it's not flowing correctly to turn the light on, which is cool. Now, why is this important? This is important because logic gates are made out of transistors, resistors, and electrical components that we just talked about. Who here has seen logic gates before? Raise your hand. Cool. How does a logic gate work, Alec?
you have an input and then an output, and I guess depending on the operation you're doing, changes the output.
Yeah, that's correct. So Alex said you have an input and an output, and then depending on the operation you're doing, it changes the output. So logic gates are used to control the flow of information, create complex circuits, and understand how computers work at a fundamental level. They carry out logical operations on single or multiple binary inputs and give only one binary output. So here we have like an inverter, which will invert the bit. So say you're putting in a 1, but your circuit needs like a 0. From that part, you put an inverter on it so you can change the signal. You have AND, NAND, OR, NOR, XOR, and XNOR. These are all logic gates that have, or logic that happens so frequently that they have their own gates to it. There are other like gates that you can make through combining different ones if you want like an exclusive output, but these are like the main ones that you use, and they can have multiple. They can have more than 2 inputs. They can have like 4, 5, 6. They can take in a lot, but they always only have 1 output, which is cool. So when creating components, these can be really tedious because, as you can see, they have lines, and then you'll connect them through wires, essentially. And drawing and mapping those wires can get really difficult whenever you're just going in and connecting them on a computer screen. So it can lead to a lot of confusion and a lot of errors. So how do developers get around this? Well, when making a component, they can use hardware description languages. These are typically like Verilog and VHDL. Those are the main ones. VHDL became really popular on the East Coast, at least, because it's used in a lot of government products. A lot of them use VHDL for programming and design. So when you go to like universities that work with the government, especially on the East Coast, they typically teach VHDL. So here at RIT, we do a lot of VHDL learning because a lot of the people that we put out go to those types of jobs where it's needed. Verilog is just a simple like syntax difference. It's nothing too crazy, but it's more popular on the West Coast because it's more used there. They're similar to a programming language in the way that you kind of have like these variables declared and like sort of sentences and working. They combine components and assign inputs and outputs and allow for synthesis of components. So combining components is, if you think you have like, say like you have some sort of like computer program and you have different functions and then you put them all into one main function. So those different functions would be in a separate VHDL file that you would import to the main VHDL file and combine and port map them. So if you go back to my slide with my information, you can see that I say like slide display, like port map name to like slide title. So that would be me port mapping the slide display, or like mapping the slide display components to my components to get the inputs and outputs from there. And that's really helpful. So it's like combining everything into like a main function, which is cool. Assigning inputs and outputs. So on logic gates, if you were to assign an input or an output, you'd have to like click on this end and click the pin and then type in like this is S and name all of the outputs here like individually and name all the pins, and then go into your pin assigner and reassign them that way based on like what you label them. But with VHDL, what you can do instead is you can just write in your entity like port, like A and B are like inputs instead of having to declare each one as an input pin on its own little device on like a signal or a circuit design, which is really nice. And then allows for synthesis of components. Say you're making like a calculator and you want to show somebody like the circuit that you made, but you don't want to show like all the 400 like AND gates or anything. What you can do is you can write it in VHDL and then synthesize it to one component and then map it that way. So you can have like the display component and the arithmetic, like the logic component and the math component, and then like an output component, and then you can connect them all and show where the output's going in like a circuit diagram instead of having to use all the logic gates. Cool. These are some common used components, like a full adder, which is up here. This is when you're adding and subtracting and changing binary numbers. This is used in like CPUs whenever, like, if you look at assembly and you're stepping through, like, instructions and, like, memory addresses, you know how it increments by, like, 4 every time? That's happening by a full adder. So every time, like, that step is happening, it's moving it in 4, and it's just designed that way. We have a decoder that's also used. All of these things are, like, used in, like, mainly, like, any type of, like, CPU or electrical device nowadays. But they're so common that they have their own designs on, like, most design softwares. So, like, you can, like, search in the bar, like, oh, a full adder with, like, 8 inputs and, like, 1 output or something like that. So they're very typical. Decoding takes in 4 outputs that are 4 inputs that are the same. They're 2, they're A and B, and then they take the regular versions and the inversions of each, and they decode. And they typically are working with an encoder inside the same program that are working in the same way, so that way everything can be a form of encryption, but not super great. And then a mux is just taking things in, and then you make choices, and then you get output. Why? Well, this is what a circuit board looks like. This is the process of designing a circuit board. So in here, sorry if it's kind of like grainy. In here, you can see like capacitors up there. And then this is like a unit that you would design in VHDL, so that way you can just give an output on there and synthesize it instead of like writing it yourself. Those are all the pin assignments. And when you make a circuit board, you want to start with like the basic of like writing VHDL or mapping out a circuit diagram, putting it all together. And then you're going to want to CAD it to see what it's going to look like. So this was in its like first like CAD version. These are capacitors, as you can see, and then there's like GPIO pins, like output pins, and then there's the final design over there with the like VGA port. Is that what that port is? Serial port, and GPIOs, and then all of like the CPU and the capacitors in the corner. Boom. And then this is a CPU. It has like an address bus with a lower register, which is just like a component that holds a certain amount of values. As you can see here, like A and all that. You have a buffer. You have a decoder. You have processor logic. I don't remember where the full adder is, but it's in there. And then accumulator, and then there's like muxes and like input registers, and then like the decimal carry, which is really cool. Oh, adder hold register. So cool. So what is hardware? I threw a lot of words at you. What is it? Well, it's a physical device like a processor or a motherboard or a power supply. It's not static, meaning that you'll need to like change out components as they degrade. You have to replace things. Like, for example, in my microcontrollers class, a lot of people like to short out the pins on there because they don't understand the point of using jumper wires, which a jumper wire is essentially you connect it to a pin and then you get the output of the pin through like the wire, so you're not actually touching everything else on the board. It's kind of like an extension of the board, so it's a lot easier for you to like take an oscilloscope to it and get the sine wave and the output signal. But a lot of the times people short those, so you have to like replace them whenever that happens, and it's a lot of work. Firmware, stored read-only memory responsible for booting the system's low-level tasks executed by the processor. Firmware is software that's embedded into hardware devices. It controls the device, how the device interacts with other devices, and the software that's put on there. So it's programmed by manufacturers of hardware components from the factory and designed to work specifically with the hardware component. Example being like BIOS or basic input output systems, controls computer on startup, interacts with other devices. This is things that like firmware typically can rely on certain hardware components. So if you're ever like looking, oh, I want to like flash this onto my computer, you might have to look into if it's compatible with your device. Like, I don't think you're going to like try to flash like a Linux system onto like a MacBook or something like that. Depending on the architecture, I don't know how well that's going to work. But firmware is sometimes like they have requirements. So whenever you're looking into new things, you should look at if your device can handle or has the processes to handle it. A lot of x86 architecture can be backwards compatible, but if you're trying to flash something that's x86 onto x32, you might be missing a couple things. Fun. I have a device, but what do I do with it? Big thing, read the numbers on the device. So typically they have like manufacturing numbers and like design numbers that are on the device, so you can like Google and search it. You can Google like the manual of the layout, the design components, and the ports. This can be helpful because most systems and most like devices have debugging pins or debugging outputs and inputs that are used for when the company has to like fix a problem. So if you're looking into like learning more about a device, you can always try to use those as like a way of getting in, but you have to know what kind of device you have and where those are. So it's very helpful if you have a manual. If you don't have a manual, what you can do is you can use like logic analysis to check some of the pins and go through some of the segments of the board. Or if you can identify components like capacitors and CPUs and different parts of it, then you can Google like those components and what boards they're on to try to get your best match, which is very helpful. You can exploit some of the ports to gain privilege that way through identifying them. And then a way this came in handy is a story about Chase. Over winter break, he got like a challenge with it was like a CD drive. Yeah, hard disk or whatever. And he was like, I have no idea what to do with this. And I was like, oh, well, there's numbers on here. Let's Google them. And then we found like the firmware for it. And we flashed it, and then he was told that he skipped a bunch of parts of the challenge, but he did get further technically, so that was cool. So yeah, cool story. Bop. GPIO, general purpose input output. They communicate to the CPU and read calculations. GPIO is an uncommitted digital signal pin on an integrated circuit that can be used as an input-output and is controllable by software. As an input, you can communicate on and off signals received from like switches or digital readings, so you can force like on and off into the device. And then for like output, you can drive outputs based on like operations happening in the CPU, like calculations to drive on an LED. So if you're looking for a pin to like be raised one or like an output to be raised on, then you can connect that to LED and you can see whenever it's raised on or off. Really cool. These are some exploits and vulnerabilities that I was like, oh, these are kind of cool. Let's talk about them. And if you have questions, ask. So Rowhammer, a lot of these are also like Intel based. So Sharad would be very happy. So Rowhammer is a vulnerability that attacks DRAM devices, where repeated access to memory can result in bit flips in adjustment rows. This means that a hacker can change the value of memory bits and parts of the memory through like just overwhelming it with different like bit flips and adjusting, which is cool. Meltdown, rogue data cache load capitalizes on non-functional execution capabilities of Intel CPUs, and it can be used to break through kernel privilege boundaries, typically to find like safeguard sensitive like secrets inside. Thunderclap is based on the Thunderbolt hardware interface produced by Intel. It can be used by hackers to access to gain physical access through the Thunderbolt port and take over a target system in just a few seconds through executing arbitrary code at the highest level of privilege, gaining access to like encryption keys and passwords, banking logins, and other data. There's like a whole bunch of like news stories about this vulnerability if you want to look into it. And there's like a Thunderclap like 2.0 where they did it again because Intel still didn't fix it. Which is cool. Speculative store bypass. This enables hackers to execute memory readers before memory write addresses are revealed, and it can be used to like leak cross-process data. It impacted Intel, AMD, and ARM processors. Foreshadow, again, affects Intel CPUs. So they use it to extract sensitive data from the CPU's like L1 data cache. And that has information accessible to all processors. They could utilize the loopholes through reading any information present in that cache, and including protected data associated with system management mode, and the kernel or and with the kernel or other like virtual machines managed by external cloud providers. The CVE was discovered on the kernel mode layer handler component of NVIDIA Windows GPU display driver. This allowed for a layer handler for a certain driver. I can't pronounce it. It's like, I can say it. It's NVLDDMKM dot system. That's what it is on the device. Inside the kernel, which doesn't correctly organize shared data. So this could result in like glitches of behavior and information, leading to potential escalation of privilege, data disclosure, and DDoS in gaming devices. And then USB Anywhere affected anything with a BMC or a baseboard management controller on Supermicro's server hardware. You could hijack thousands of server boards and push unauthenticated network traffic and plain text authentication and bypass most authentications on the server with like weak encryption for remote connections, which is cool. It is scary, but it's cool. Cool. These are techniques. Fault injection. Guys, if I can fault. Fault injection is typically carried out prior to deployment to uncover any potential faults that may have been introduced during production. Similarly to stress testing, fault injection testing is used to identify specific weaknesses in hardware or software systems so they can be fixed or avoided. If this isn't done properly, you can also do fault injection. So there are different types of fault injection. Voltage glitching is performed by momentarily dropping supply voltages during the execution of specific operations. Clock glitching is performed by altering clock timing to violate setup and hold their requirements of the hardware, such as through the insertion of like a clock glitch pulse in between normal time clock pulses. Electromagnetic fault injection is performed by generating localized, short-duration, high-intensity electromagnetic pulses that induce currents within internal chip circuitry. And optical fault injection uses infrared lasers and usually requires a chip decapsulation to expose the silicon die. Many classes of fault injection attacks require hardware modification of the target device. For example, voltage glitches attacks usually require the removal of power filtering capacitors, which grants the attacker more fine-grained control over the processor's voltage input. All glitching attacks require the use of an apparatus whose purpose is to accurately inject the fault condition, such as tools like NUAE's Chip Whisperer and Chip Shouter or Riskier's Spider are commonly used to conduct fault injection attacks. An attacker can also build their own custom glitching harness. I think RITSEC should buy one. We develop our own. That'd be cool. The cost of a tool has continued to the cost of such tooling has continued to decline, and today's attacks are feasible with under $100 worth of equipment. So that's cool. There's also side channel attacks. A side channel attack is a security exploit that attempts to extract secrets from a chip or a system. This can be achieved by measuring or analyzing various physical parameters. These attacks pose a serious threat to modules that integrate cryptographic systems. Cool. A timing attack. This analyzes the time a system spends executing cryptographic algorithms, and then once you figure out the time, you can inject your processes in between, and so it just gets lost in the section, which is cool. Electromagnetic attack measures and performs a signal analysis on the electromagnetic radiation emitted from a device. Simple power analysis directly observes the power of electromagnetic variations of a cryptographic system during operation. Differential power analysis obtains and analyzes detailed statistical measurements across multiple operations, and template attacks recover cryptographic keys by exploiting an identical template device and comparing side channel data. Questions? I figured you would have a question. Yeah?
I do have questions. But...
Okay, we'll go with Alec first. Yes, Alec?
I was just wondering how, like on a hardware level, or possibly like a firmware level, how like some of these devices are secured. Because like I assume it's different from your traditional like Windows or like Linux operating system.
So typically it comes in at like the firmware level, because so for like hardware, like boards, they have like for like voltage glitching and everything, they have capacitors and certain different components in there to make sure that like if somebody's trying to like voltage glitch or do something, that they can regulate their own voltage to the working speed that they need, or like inductors to stop extra voltage from coming in and like frying the board or something. So that's on like a component level. For firmware, I don't know too much about on like the firmware level. Kenny, do you know anything?
It depends.
I'm gonna give you that.
It's a very it depends. There's kind of like just not common theme, but there's kind of common theme that is somewhat different. I consider it as this is an accuracy device, right? Basically mentioned capacitors kind of program like fault protection, but also like hardware level protection, right? There's shielding, monitoring, rewards, there's building, and all that stuff, or like instruction. On the actual microprocessor cells and in the flash, there's hardware implementations so that people can read automatically. Also, there's like there's a certain amount of possibility to like PCB layout because like you mentioned, whatever there is for debug. A lot of companies will just kind of randomize the actual amounts of PCB, but then you see it's kept at only 85. It goes I know it's seeing those debug. I see just figuring it out, but what else? Rockets, physical shielding. We talked about the ball protection, the capacitors, having an internal like clock source. There's like a lot of real clock, right? So you have temporary all in clock. So as I said, I really require clock. So when coming in, I have it internal clock on board, right? However, again, you have support and using chip facility for that clock, you can cut it off and go for but
In terms of like some like conferences will have like hardware CTFs. Typically for like them, they'll get rid of anything that like any product number or anything that's like on the board, and then you'll have to figure that out yourself. So also like obscuring like where the product is made, and like that information, or like some like the manuals don't have everything, so sometimes yeah.
Yeah, I'm sorry. Here in the metric Kasey is correct. A lot of companies will actually from the silk, not silk, but the one microphone would kind of obscure part. But
Cool. Any other questions? No? Anybody from the hardware mentorship have a question? Dan does not have a question.
I'm surprised.
Chase K, you have a question?
Speaking of hardware, do you happen to know what this device is called?
No.
Pop it up, Kasey.